I'd like to welcome our second and final plenary to the stage. Up next is Yann LeCun. He's Chief AI Scientist at Meta and Professor at NYU. Now, Yann was the founding director of MetaFair and of the NYU Center, I should say, for Data Science. He works primarily in a number of fields: machine learning, computer vision, mobile robotics, and computational neuroscience. In 2019, Yann won the prestigious ACM Turing Award for his work on AI, and he's of course a member of the US National Academies and the French Académie de Sciences. A warm welcome to you, Yann. Good to have you.
Thank you very much. A real pleasure to be here. Last time must have been before COVID or something. There's going to be some connection a little bit with what Bernard just talked about. And what I'm going to talk about is all the stuff that Mike Jordan earlier today told you you shouldn't be working on. So as a matter of fact, we do need human-level AI. And it's not just because it's an interesting scientific question. It's also sort of a product need. We are going to be wearing smart devices like smart glasses and things of that type in the future. And in those smart devices, we'll be able to access AI assistants that will be with us at all times. And we'll be interacting with them either through voice or through electromyograms, EMG. The glasses will eventually have displays, although currently they don't. And we need those systems to have human-level intelligence because that's what we're the most familiar interacting with. We're familiar with interacting with other humans. We are familiar with the level of intelligence that we expect in a human, and it would be more, easier to interact with systems that have kind of similar forms of intelligence. Those ubiquitous assistants are going to mediate all of our interactions with the digital world, and that's why we need them to be easy to use for a wide population that is not necessarily familiar with using technology. Okay, but the problem is machine learning sucks compared to what we observe in humans and animals. We don't really have the techniques that would allow us to build machines that have the same type of learning abilities and common sense and understanding of the physical world. So animals and humans have background knowledge that allows them to learn new tasks extremely quickly, understand how the world works, being able to reason and plan, and that's based on what we call common sense. It's not a very well-defined concept. And our behavior and behaviors of animals are driven by objectives, essentially. So I'm going to argue that the type of AI systems that we have at the moment, or that everybody is playing with, almost everybody is playing with, do not have the right characteristics for what we want. And the reason is they basically produce one token after the other autoregressively, right? So you have a sequence of tokens, which are subword units, but it doesn't matter what they are, a sequence of symbols. And then you have a predictor that is repeated over the sequence that basically take a window of previous tokens and predict the next token. And the way you train those systems is that you put the sequence at the input, and I really apologize for this. I'm going to perhaps change the resolution of the screen so that we don't have this constant flashing. Hang on just 1 second. Okay, not sure this is better, but hopefully. All right. So the way those things are trained is you take a sequence and you basically train the system to just reproduce its input on its output. And because it has a causal structure, it cannot cheat and use a particular input to predict itself. It has to only look at the symbols that are to the left of it. That's called a causal architecture. So that's very efficient. This is, what people call a GPT, general purpose transformer, but you don't have to put transformers in it. This could be anything. It's just a causal architecture. And I'm afraid I haven't fixed the flashing. Anyway, so the way you train those systems, then you can use it to generate text by just auto-regressively producing a token, shifting it into the input, and then producing the second token, shifting that in, etc. That's auto-regressive prediction, not a new concept at all, obviously. And there's an issue with this, which is that that process is basically divergent. Every time you produce a token, there is some chance that the token is not within the set of reasonable answers and take you outside the set of reasonable answers. And if it does that, there is no way to fix it afterwards. And if you assume there is some probability for that, wrong token, for wrong tokens to be generated, and the errors are independent, which of course they're not, then you get exponential divergence, which is why we have with those models hallucination issues. But we're missing something really big because, never mind trying to reproduce human intelligence, we can't even reproduce cat intelligence or rat intelligence, let alone dog intelligence. They can do amazing feats. They understand the physical world. Any house cat can plan very highly complex actions. And they have causal models of the world. Some of them know how to open doors and taps and things of that type. And in humans, a 10-year-old can clear up the dinner table and fill up the dishwasher without learning, zero shot. The first time you ask the 10-year-old to do it, he or she will do it. Any 17-year-old can learn to drive a car in 20 hours of practice. But we still don't have robots that can act like a cat. We don't have domestic robots that can clear up the dinner table. And we don't have level 5 self-driving cars, despite the fact that we have hundreds of thousands, if not millions of hours of supervised training data. Okay, so that tells you we're missing something really big. Yet we have systems that can pass the bar exam, do math problems, prove theorems, but no domestic robots. So we keep bumping into this paradox called the Moravec paradox, right? Things that we take for granted because humans and animals can do it, we think it's not complicated. It's actually very complicated. And the stuff that we think is uniquely human, like manipulating and generating language, playing chess, playing Go, playing poker, producing poetry and this kind of stuff, turns out to be easy, relatively. Okay, and perhaps the reason for this is this very simple calculation. A typical LLM nowadays is trained on the order of 30 trillion tokens, 3 10 to the 13 tokens. That's 2 to the 13 words, roughly. Each token is about 3 bytes. So the data volume is roughly 10 to the 14 bytes. It would take any of us almost 500,000 years to read through all that material. It's basically all the publicly available text on the internet. Now, consider a human child. A 4-year-old has been awake a total of 16,000 hours, which, by the way, is only 30 minutes of YouTube uploads. We have 2 million optical nerve fibers, each of which carries about 1 byte per second, maybe a bit less, but it doesn't matter. So the data volume is about 10 to the 14 bytes. In 4 years, a 4-year-old child has seen as much data as the biggest LLM in the form of visual perception. And for blind children, it's touch. It's the same kind of bandwidth. That tells you a number of things. We're never going to get to human level intelligence by just turning on text. It's just not happening. Despite what some people who have a vested interest in this happening are telling us that we're going to reach PhD level intelligence by next year. It's just not happening. We might have PhD level in some subfield, in some area, some problems like chess playing, but more of them. as long as we train those systems specifically for those problems, as Bernard was explaining with the visual illusions, there are a lot of problems of this type. When you formulate a problem, you pose a problem to an LLM, and if the problem is kind of a standard puzzle, the answer will be regurgitated in just a few seconds. If you change the statement of the problem a little bit, the system will still produce the same answer that it had before because it has no real mental model of what goes on in the puzzle. So how do humans, infants, learn how the world works? And infants accumulate a huge amount of background knowledge about the world in the first few months of life. Notions like object permanence, solidity, rigidity, natural categories of objects. Before children understand language, they do understand the difference between the table and the chair. That kind of develops naturally. And they understand intuitive physics notion like gravity, inertia, and things of that type around the age of 9 months. So it takes a long time. Observation mostly, until 4 months, because babies don't really have any influence on the world before that. But then through interactions. But the amount of interaction that's required is astonishingly small. So if we want AI system that can eventually reach human level, it might take a while. We call this advanced machine intelligence at Meta. We don't like the term AGI, artificial general intelligence, the reason being that human intelligence is actually quite specialized, and so calling it AGI is kind of a misnomer. So we call this AMI. We actually pronounce it ami, which means friend in French. So we need systems that learn world models from sensory input, basically mental models of how the world works that you can manipulate in your mind, learn intuitive physics, from video, let's say. Systems that have persistent memory, systems that can plan actions, possibly hierarchically, so as to fulfill an objective, and systems that can reason. And then systems that are controllable and safe by design, not by fine-tuning, which is the case for LLMs. Now, the only way I know to build systems of this type is to change the type of inference that current AI systems perform. So right now, the way an LLM performs inference is by running through a fixed number of layers of a neural net, a transformer, then producing a token, injecting that token on the input, and then running through a fixed number of layers again. And the problem with this is that if you ask a simple question or a complex question and you ask the system to answer by yes or no, like does 2 and 2 equal 4, yes or no, or does P equal NP, yes or no, it's going to spend the exact same amount of computation to answer those two questions. So people are being kind of cheating and telling the system, well, explain, it's the chain of thought trick. You basically have the system produce more tokens, so that is going to spend more computation answering the question. But that's kind of a hack. The way a lot of inference in statistics, for example, that's going to make Mike happy, actually. The way inference works is not that way in classical AI, in statistics, in structural prediction, a lot of different domains. The way it works is that you have a function that measures the degree of compatibility or incompatibility between your observation and a proposed output. And then the inference process consists in finding the value of an output that minimizes this incompatibility measure. Okay? Let's call it an energy function. So you have an energy function, okay, represented by this square box here on the right, when it doesn't disappear. And the system just performs optimization for doing inference. Now, if the inference problem is more difficult, the system will just spend more time performing inference. In other words, it will think about complex problems for longer than simple ones, for which the answer is pretty obvious. And this is really a very classical thing to do. In classical AI is all about reasoning and search and therefore optimization. Pretty much any computational problem can be reduced to an optimization problem, essentially, or a search problem. It's also very classical in probabilistic modeling, like probabilistic graphical models and things of that type. So this type of inference would be more akin to what psychologists call system 2 in sort of human mind, if you want. System 2 is when you think about what action or sequence of actions you're going to take before you take them, you think about something before doing it, and then system 1 is when you can do the thing without thinking about it. It becomes sort of subconscious. So LLMs are system 1. What I'm proposing is system 2. And then the appropriate sort of semi-theoretical framework to explain this is energy-based models, which I'm not going to have time to get into too much detail. But basically, you capture the dependency between variables, let's say observations x, and outputs y, through an energy function that takes low value when x and y are compatible, and then larger values when x and y are not compatible. You don't want to just compute y from x, as we just saw. You just want an energy function that measures the degree of incompatibility, and then, given an x, find a y that has low energy for that x. Okay, so now let's go a little bit into the details of how this type of architecture can be built. So essentially, and how it kind of relates to thinking or planning. So a system would look like this. You get observation from the world, you go through a perception module that produces an estimate about the state of the world, but of course, the state of the world is not completely observable, so you may have to combine this with a memory, the content of a memory that contains your idea of the state of the world you don't currently perceive. And the combination of those two goes into a world model. So what is a world model? World model is given a current estimate of the state of the world, which is in an abstract representation space, and given an action sequence that you imagine taking, your world model predicts the resulting state of the world that will occur after you take that sequence of actions. Okay? That's what a world model is. If I tell you, imagine a cube floating in the air in front of you, okay, now rotate this cube by 90 degrees around a vertical axis. What does it look like? It's very easy for you to kind of have this mental model of a cube rotating.
Sorry, excusez-moi. Est-ce qu'on peut baisser la fréquence de balayage de votre...
Ok.
C'est ça qui pose problème.
C'est apparemment la fréquence de balayage.
Vous devez être en 60 Hz. Il faudrait passer à 50 ou 25.
Oui, mais pourtant, il ne me laisse pas le sélectionner.
Dans Aja...
attendez. Ah oui, le voilà.
Voilà, 60 Hz.
Ok. 50.
50 par exemple. Ça devrait être bon.
Ok.
Désolé, je préférais vous interrompre.
Pas de problème. Okay, hopefully, all right. Let's hope this will be more stable. Okay, merci. 50 hertz, not 60 hertz. Okay, so what you can do now is feed, okay, hang on. I'm gonna make a more radical choice here. Okay, this doesn't look like it was a good idea. Oh, I know. Well, that's nice.
Par contre, toujours en 25 ou 50.
Non, là, je peux pas changer. Okay, I think we're going to have human level intelligence before we have audio video that actually works. Okay, so if we have this world model, which is able to predict the result of a sequence of actions, we can feed it to an objective, which is a task objective that measures to what extent the predicted final state satisfies a goal that we set for ourselves. It's just a cost function. And we also can set some guardrail objectives. Think of them as constraints that need to be satisfied for the system to behave in a safe manner, right? So those guardrails will be explicitly implemented. And the way the system proceeds is by optimization. It's looking for an action sequence that minimizes the task objective and the guardrail objectives at runtime, okay? We're not talking about learning here. We're just talking about inference. And that will guarantee the safety of the system because the guardrails guarantee safety, and there is no way you can jailbreak that system by giving it a prompt that will, have it escape its guardrail objectives. The guardrail objectives will be just hardwired. They might be trained, but hardwired. Now, a sequence of actions should probably use a single world model that you use repeatedly over multiple time steps. Okay, so you have a world model, you feed it the first action, it predicts the next state, and the second action predicts the second next state. You can have guardrail cost and objective task objectives along the trajectory. I'm not specifying what optimization algorithm we can use. It doesn't really matter for the discussion that we have. If the world happens not to be completely deterministic and predictable, our world model may need to have latent variables to account for all the things about the world that we do not observe, and that makes our prediction basically inexact. And ultimately, what we want is a system that can plan hierarchically. So something that may have several levels of abstraction in such a way that at the low level, we plan low-level actions, like basically muscle control, but at a high level, we can plan abstract macro action, where the world model predicts at longer time steps, but in a representation space that is more abstract and therefore contains fewer details. So if I'm sitting at my office at NYU and I decide to go to Paris, I can decompose that task into two subtasks. Go to the airport and catch a plane. Okay, now I have a sub-goal, going to the airport. I'm in New York City, so going to the airport consists in going down on the street and hailing a taxi. How do I go down in the street? Well, I need to get to the elevator, push the button, go down, go out the building. How do I go to the elevator? Well, I need to stand up from my chair, pick up my bag, open the door, walk to the elevator, avoid all the obstacles, and then at some point I get to a level where I don't need to plan, I can just take the actions. But we do this type of hierarchical planning absolutely all the time. And I tell you, we have no idea how to do this with learning machines. Almost every robot does hierarchical planning, but the representations at every level of the hierarchy are handcrafted. What we need is to train an architecture perhaps of the type that I'm describing here so that it can learn abstract representations, not just of the state of the world, but also prediction, world models that predict what's going to happen, but also abstract actions at various levels of abstraction. So we can do this hierarchical planning. Animals do this, okay? Humans do this very well. We're completely incapable of doing this with AI systems today. If you're starting a PhD, great topic. It might take more than 3 years. So I mean, with all those reflections, about 3 years ago, I wrote a long paper where I kind of explained sort of where I think AI research should be focusing on. So this was before the whole ChatGPT craze. I haven't changed my mind about this. ChatGPT hasn't changed anything. We were working on LLMs before that, so we knew what was coming anyway. This is the paper, A Path Towards Autonomous Machine Intelligence, that we now call Advanced Machine Intelligence, because autonomous just scares people. And it's on open review, it's not on archive. And there's various versions of this talk that I've given various ways. Okay, so a very natural idea for getting systems to understand how the world works is using the same process that we use to train system for natural language and apply this to, let's say, video. Okay, if a system is capable of predicting what's going to happen in a video, you show it a short segment of video and you ask it to predict what's going to happen next. Presumably, it would have understood the underlying structure of the world. And so training it to make that prediction might actually cause the system to understand the underlying structure of the world. It works for text because predicting words is relatively simple. Why is predicting words simple? Because words there's only a finite number of possible words, certainly a finite number of possible tokens. And so we can't predict exactly which word will follow another word, or what word is missing in the text, but we can produce a probability distribution or a score for every possible word in the dictionary. We cannot do this for images, for video frames. We do not have good ways of representing distributions over video frames. Every attempt to do this basically bumps into mathematical intractabilities. And so you could try to get around the problem using, statistics and the math that was invented by physicists, variational inference and all that stuff. But in fact, it's better to just throw away the entire idea of doing probabilistic modeling and just say, I just want to learn this energy function that tells me whether my output is compatible with my input, and I don't care if this energy function is a negative log of some distribution. And so the reason we need to do this, of course, is because we cannot predict exactly what's going to happen in the world. There is a whole set of possible things that may happen. And if we train a system to just predict one frame, it's not going to do a good job. So the solution to that problem is a new architecture I call Joint Embedding Predictive Architecture, or JEPA. And that's because generative architecture simply do not work for producing videos. You may have seen video generation systems that produce pretty amazing stuff. There's a lot of hacks that go behind them, and they don't really understand physics. They don't need to. They just need to predict pretty pictures. They don't need to actually have kind of accurate model of the world. Okay, so here's what the JEPA is. The idea is that you run both the observation and the output, which is the next observation, into an encoder, so that the prediction does not consist in predicting pixels, but basically predicting an abstract representations of what goes on in the video or anything, okay? So let's compare those two architectures. On the left, you have generative architectures. You run X, the observation, through an encoder, and perhaps through a predictor or a decoder, and you make a prediction for Y, okay? That's straightforward prediction. And then on the right, this JEPA architecture, you run both X and Y through encoders, which may be identical or different. And then you predict the representation of Y from the representation of X in this abstract space. This will cause the system to basically learn an encoder that eliminates all the stuff that you cannot predict. And this is really what we do. There's no way that, if I observe the left part of this room here and I kind of pan the camera towards the right, there's no way any video prediction system, including humans, can predict what every one of you looks like, or predict the texture on the wall, or the texture of the wood on the hardwood floor. There's a lot of things that we just simply cannot predict. And so instead of insisting that we should make a probabilistic prediction about stuff that we cannot predict, let's just not predict it. Learn a representation in which all of those details are essentially eliminated so that the prediction is much simpler. It may still need to be non-deterministic, but at least we'll simplify the problem. So there's various flavors of those JEPAs, which I'm not going to go into, some of which have latent variables, some of which are action conditioned. So I'm going to talk about the action condition, because that's the most interesting one, because they really are world models, right? So you have an encoder, X is current state of the world, or current observation, SX is current state of the world. You feed an action to a predictor, which you imagine taking, and the predictor, which is a world model, predicts the representation of the next state of the world. And that's how you can do planning. Okay, so we need to train those systems, and we need to figure out how to train those JEPA architectures. And it turns out to not be completely trivial, because you need to train the cost function in this JEPA architecture that measures the divergence, essentially, between the representation of Y and the predicted representation of Y. We need this to be low on the training data, but we also need it to be large outside the training set, okay? So this is, this kind of energy function here that has kind of contours of equal energy. We need to make sure the energy is high outside of the manifold of data. And I only know two classes of methods for this. One set of methods is called contrastive. It consists in having data points, which are those dark blue dots, pushing down the energy of those, and then generating those flashing green dots, and then pushing the energy up. The problem with this type of method, contrastive method, is that they don't scale very well in high dimension. If you have too many dimensions in your space of Y, you're going to need to push up in lots of different places, and it doesn't work so well. You need a lot of contrastive samples for this to work. There's another set of method that I call regularized method, and what they do is they use a regularizer on the energy so as to minimize the volume of space that can take low energy. Okay, so that leads to two different types of learning procedure. One learning procedure which is contrastive, where you need to generate those contrastive points and then push the energy up to some loss function. And the other one is some regularizer that is going to sort of shrink wrap the manifold of data so as to make sure that the energy is higher outside. So there's a number of techniques to do this. I'll describe just a handful. And the way we started testing them several years ago, maybe 5-6 years ago, was to train them to learn representations of images. So you take one image, you corrupt it or transform it in some ways, and you run the original image and the corrupted version in identical encoders, and you train a predictor to predict the representation of the original image from the corrupted one. Once you are done training the system, you remove the predictor, and you use the representation at the output of the encoder as input to a simple, like a linear classifier or something of that type that you train supervised so as to verify that the representations that are learned are good. And this idea is very old. It goes back to the 1990s and things like we used to call Siamese networks and some more recent work on those joint embedding architectures. And then adding the predictor is more recent. So SimClear, which is from Google, is a contrastive method derived from Siamese nets. But again, the dimension is restricted. So the regularized method worked the following way. You try to have some sort of estimate of the information content coming out of the encoders. And what you need to do is prevent the encoder from collapsing. There's a trivial solution of training a JEPA architecture where the encoder basically ignores the input, produces a constant output, and now the prediction error is 0 all the time, okay? And obviously that's a collapsed solution that is not interesting. So you need to prevent the system from collapsing, and which is the regularization method I was talking about earlier. And an indirect way of doing this is maintain the information content coming out of the encoder, okay? So you're gonna have a training objective function, which is a negative information content if you want, because we minimize in machine learning, we don't maximize. One way to do this is to basically take the vectors, representation vectors that come out of the encoder over a batch of samples and make sure they contain information. How can you do this? You can take that matrix of representation vectors and compute the product of that matrix by its transpose. You get a covariance matrix. And you try to make that covariance matrix equal to identity. So there's a bad news with this, which is that this basically approximates the information content by making very strong assumptions about the nature of the dependencies between the variables. And in fact, it's an upper bound on information content, and we're pushing it up, crossing our fingers that the actual information content, which is below, is going to follow, okay? So it's slightly irregular, theoretically, but it works, all right? So again, you have a matrix coming out of your encoder. It's got a number of samples, and each vector is a separate variable. What we're gonna try to do is gonna try to make each variable individually informative. So we're gonna try to prevent the variance of the variable from going to 0, force it to be 1, for example. And then we're going to decorrelate the variables with each other. And that means computing the covariance matrix of this matrix is transpose multiplied by itself, and then try to make the resulting covariance matrix as close to the identity matrix as possible. There are other methods that try to make the samples orthogonal, not the variables. Those are sample contrastive methods, but they don't work in high dimension and they require large batches. So we have a method of this type called VicReg That means variance, invariance, covariance, regularization, and it's got particular loss functions for this covariance matrix. There's been kind of similar methods proposed by Yima and his team called MCR squared, and then another method by some colleagues from NYU called MMCR from neuroscience. So that's one set of methods, and I really like those methods, and I think, and they work really well. I expect to see more of them in the future. But there's another set of methods that to some extent has been slightly more successful over the last couple of years, and those are based on distillation. So again, you have two encoders. It's still a joint embedding predictive architecture. You have two encoders. They kind of share the same weights, but not really. So the encoder on the right gets a version of the weights of the encoder on the left that are obtained through a exponential moving average, okay, a moving average. So basically you force the encoder on the right to change its weight more slowly than the one on the left, and for some reason that prevents collapse. There's some theoretical work on this. In fact, this is one that Jean-Paul's just finished writing. But it's a little bit mysterious why this works, and frankly I'm a little uncomfortable with this method, but we have to accept the fact that it actually works. If you're careful. You know, real engineers build things without necessarily knowing why they work. That's good engineers. And then the usual joke in France that everybody here should learn is that students that come out of École Polytechnique, when they build something, it doesn't work, but they can't tell you why. Sorry about that. I didn't study here, you can tell. Okay, let me switch ahead, skip ahead a little bit in the interest of time, because we wasted a bit of time. Okay, so there's a particular way of implementing this idea of distillation called IJPA. There's another one called Dino, or Dino, which I skipped a little bit. So Dino, it's V2, people are working on V3. This is a method produced by some of my colleagues at FAIR Paris. A team led by Maxime Ocab. And then a slightly different version called IJPA, VJPA, by also FAIR, people in Montreal and Paris mostly. So no need for negative samples there. And those systems learn generic features that you can then learn for any downstream task, and the features are really good. So this works really well. I'm not going to bore you with details because I don't have time. More recently, we worked on a version of this for video. So this is a system that takes a chunk of 16 frames from video, and you take those 16 frames, run them to an encoder, and then you corrupt those 16 frames by masking some parts of it, run them to the same encoder, and then train a predictor to predict the representation of the full video from the one that is partially masked or corrupted. And so again, this is a group of researchers at FAIR in Paris and Montreal. And this works really well in the sense that you learn features that you can then feed to a system that can classify actions in videos, and you get really good results with these methods. Again, I'm not going to bore you with details. But here is a really interesting thing. This is a paper that we just submitted. If you show that system videos where something really strange happens, that system actually is capable of telling you, my prediction error is going through the roof. There's something strange going on in that window. So you take a video, and you take the 16 video frame window, you slide it over the video, and you measure the prediction error of the system. And if something really strange happens, like an object spontaneously disappears or changes shape, the prediction error shoots up. So what that tells you is that that system, despite its simplicity, has learned some level of common sense. It can tell you if something really strange in the world is happening. Lots of experiments to show this in sort of various contexts for various types of intuitive physics, but I'm going to skip to this latest work, Dino world model. So this is using Dino features and then training a predictor on top of it, which is action condition, so that it's a world model that we can use for planning. And this is a paper that is on arXiv. There's a website also that you can look at. The URL is at the top here. So basically, train a predictor using, a picture of the world that you run through a Dino encoder, and then an action that maybe a robot takes. So you get the next frame of that video, next image from the world, run this through the Dino encoder, and then train your predictor to just predict what's going to happen given the action that was taken. Okay, very simple. To do planning, you observe an initial state, run it through the Dino encoder, then run your world model multiple time steps with imagined actions. Then you have a target state, which is represented by a target image, for example. You run it through the encoder, and then you compute the distance in state space between the predicted state and the state representing the target image. And the planning consists in just, through optimization, finding a sequence of actions that minimizes that cost at runtime, okay, at inference time. You know, people are all excited about test time computation and blah, 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 as if it was something new. This is completely classical in optimal control. This is called model predictive control. It's been around with us for about the same time that I've been around, all right? The first paper is on planning using models of this type, using optimization, are from the early 60s. The ones that actually learned the model are more recent. They're more from the 70s, from France, actually. It's called IDECOM. Some people in optimal control might know about this. But it's a very simple concept. This works amazingly well. So let me skip to the video, because, okay, so let's say you have this little T shape, and you want to push it into a particular position. And so you know which position it has to go to, because you put an image of that position, run it to the encoder, and that gives you a target state in representation space. Let me play that video again. Okay, so at the top, you see what actually happens in the real world when you take a sequence of actions that is planned. And what you see at the bottom is the internal mental prediction of what the system, of the sequence of actions that the system was planning. And this is run through a decoder that produces a pictorial representation of the internal state, but that is trained separately. There's no image generation. Let me skip to the more interesting one. So here is one where you have an initial state, which is a bunch of blue chips randomly thrown on the floor. And the target state is at the top. And what you see here are the actions that are result from planning and the robot accomplishing those actions. The dynamics of this environment is actually fairly complicated because those blue chips kind of interact with each other and everything. The system has just run this through observing a bunch of state action, next state. And this works in a lot of situations for arms and moving through mazes and pushing a T around and things like that. So, okay, and I'm not sure why it came back. We've applied kind of similar idea to navigation, but in the interest of time, I'm just going to skip. So this is basically sequences of videos where a frame is taken at one time, and then the robot moves, and through odometry, by how much the robot has moved, you get the next frame. And so you just train the system to predict what the world is going to look like if you take a particular motion action. And what you can do next is you can tell the system, navigate to that point, and it will do it and avoid obstacles on the way. This is very new work. But let me go to the conclusion. So I'm having a number of recommendations. Abandon generative models. The most popular method today that everybody is working on. Stop working on this. You work on JPAs. Those are not generative models. They predict in representation space. Abandon probabilistic models because it's intractable. Use energy-based models. Mike and I have had a 20-year contentious discussion about this. Abandon contrastive methods in favor of those regularized methods. Abandon reinforcement learning, but that I've been saying for a long time. We know it's inefficient. You have to use reinforcement learning really as a last resort when your model is inaccurate or your cost function is inaccurate. But if you are interested in human-level AI, just don't work on LLM. There's no point. I mean, in fact, if you are in academia, don't work on LLM because you're in competition with hundreds of people with tens of thousands of GPUs. There's nothing you can bring to the table. Do something else. there's a number of problems to solve. Training those things with large-scale data, blah, blah, blah. Planning algorithms are kind of inefficient. We have to come up with better methods. So if you are like into optimization, applied math, it's great. JPA with latent variables, planning under uncertainty, hierarchical planning, which is completely unsolved. Learning cost module, because probably most of them you can't build by hand, you need to learn them. And then there is issues of exploration, etc. Okay, so in the future, we'll have universal virtual assistants. They'll be with us at all times. They will mediate all our interaction with the digital world. We cannot afford to have those systems come from a handful of companies from the west coast of the US or China, which means the platforms on top of which we build those systems need to be open source and widely available. They are expensive to train, but once you have a foundation model, fine-tuning it for a particular application is relatively cheap, and a lot of people can afford to do this. So the platforms need to be shared. They need to speak all the world's languages, understand all the world's cultures, all the value systems, all the centers of interest. No single entity in the world can train a foundation model of this type. This probably will have to be done in a collaborative fashion or distributed fashion. Again, some work for applied mathematicians who are interested in distributed algorithms for large-scale optimization. And so open source AI platforms are necessary. The danger I see in Europe and in other places is that geopolitical rivalry will entice governments to basically make the release of open source model illegal, because they are under the impression that a country will stay ahead if it keeps its science secret. That would be a huge mistake. When you do research in secret, you fall behind. It's inevitable. What will happen is that the rest of the world will go open source and will overtake you. That's currently what's happening. The open source models are overtaking, slowly but surely, proprietary models. Thank you very much.